Hi, so in this video I'm looking at questions 14 to 17 in the genetic problems assignment 3, and these questions are to do with particular type of inheritance called sex linkage. Sex linkage. So the first thing you need to know about is how kind of being male or female is inherited. So what you should know by now is that you have 23 pairs of chromosomes in your cells normally, and out of those 23 pairs, the first 22 are known as autosomes. And these chromosomes code for everything and anything from kind of the shape of your ear to the color of your eyes to the color of your hair, I do not know, shape of your thumb, so on and so forth. So these chromosomes code for everything pretty much apart from sex, meaning being male or female. And then this last pair of chromosomes, just one pair, which is specifically designed to code for being a male or a female. So they code for sex, right? So being male or female. And here you've got two options. So if in that pair of sex chromosomes you have two chromosomes known as XX, that means you are female. And if you have two chromosomes which look a little bit different to each other, so they're known as X and Y, they code for being a male. So basically whether you have two chromosomes which are the same in that pair, then you're female. If two chromosomes are different, then you are a male. So why they're known as XX and XY? Well, that's because when people looked under microscope at this particular pair of chromosomes, then the two X chromosomes look like kind of traditional shape of a chromosome, which overall looks a little bit like an X. And this is sort of picture you would find in my explanation of mitosis and meiosis, etc. But in a male, one of his chromosomes looked a little bit like that. So it had sort of, it looks like it's got like a little leg kind of missing. So overall shape, resembled letter Y, and that's how those kind of symbols came about. So let's take a simple monohybrid cross like we did before. So you have male, XX, this is crossed with a female, XY. Don't get confused, right? So XX, this is for the chromosome, that little X is to show that it's a cross. So the same as before, gametes in a male. Oh, I've gone wrong, haven't I? Good job, I've just noticed that. So this is female and male. Ta-da! So it's going to be X and a Y. Shouldn't rush, you see? That's the problem with genetics. You do one little symbol wrong somewhere and it can completely throw you. Okay, so there you go. So these are my two male gametes. These are my two female gametes. That means that in a male, when they're producing sperm, roughly half of their sperm is going to contain X chromosome, the other half is going to contain Y chromosome. And when females produce eggs, all of the eggs contain X chromosome. So then I'm back to my Punnett square. Again, simple grid, as if you were playing noughts and crosses. So X and a Y here, X and X here. So XX, XY, XX, XY, XY. So you can clearly see you've got 50-50% situation. So in your first generation, so if you started with your two parents, first generation, 50% of the outcome is going to be male, and then another 50% of the outcome is going to be female. Right, so that's what genetics kind of tells us. Okay, so this is fine, seemingly fairly easy. So what about the questions in the assignment? Because they look a lot more complicated than that. Well, this is because they are dealing with, as I said, a particular type of inheritance called sex linkage. And what sex linkage essentially is when within your sex chromosome, so in the pair of sex chromosomes, you have some kind of mutation embedded. And in reality, that mutation, so let's say you have a normal chromosome, X chromosome here, and everything is normal and healthy, but you might have a second X chromosome, and that has got some kind of fault in it, some kind of mutation in it. So let me highlight it in red. So that mutation is embedded into one of the sex chromosomes, and because it's embedded in sex chromosome rather than in a one of the autosomes, that means that that mutation is going to be passed on in the same way as sex. So that's why we're calling it sex linkage, because it's kind of linked to sex chromosome, embedded in this X chromosome. Now, you might also have situation where you can have Y chromosome being healthy, or in another person, obviously a single person will just have a single Y chromosome, so we're talking about two different individuals here. So you might have healthy Y chromosome, or again, you might have a Y chromosome with a mutation in it. Yeah? So that would be another example of sex linkage. But for the purposes of the assignment, all the questions in your assignment, question 14 to 17, they all deal with situation where mutation is found on the X chromosome. Okay, so forget about this scenario. It does exist, but the questions are not asking you about that scenario. So they all deal with mutation being found on the X chromosome. Okay, chromosome. So just be aware of that fact when you're solving those problems. Okay, so next we're going to look at a specific example, and this particular example is going to deal with a condition which is found in humans, and it's a type of sex-linked condition, and it's known as hemophilia. So that's my example, hemophilia. So this is a sex-linked condition. So some of you might have heard about hemophilia before. Maybe some of you never heard of it before. And it's a pretty rare condition. It's not very widespread. And it's a genetic disorder, so it's not something you can kind of treat by operating on a person, because that's a mutation which is going to be found in every cell of this person's body, something they inherit. And this particular condition is characterized by the fact that this person's blood cannot clot, right? So normally, you remember, if you have a cut, then you've got this particular type of sort of structures within your red blood, which are called platelets, and they produce proteins which make blood thicken and blood clots, and therefore you stop bleeding pretty quickly. Well, in the people who's got hemophilia, that kind of chain of events where particular protein is produced and thickens the blood, it just doesn't happen. So you can imagine any pretty trivial cut can actually end up with a pretty significant blood loss. So these people bruise very easily. They if they cut themselves, that the blood is going to take a really long time to kind of stop from bleeding. And in the past, very rarely people with hemophilia would survive beyond kind of early teens or childhood, essentially. Nowadays, what happens with people with hemophilia, they have to have injections of these particular proteins, so-called clotting factors, and it basically means that their blood is unable to clot. But they have to obviously keep on injecting these clotting factors throughout their life in order to avoid severe symptoms. So not very pleasant diseases, you can imagine. And so what we're going to do as far as kind of genetic crosses are concerned, we're going to use a couple of letters. So we're going to use capital H for the normal gene. So this is going to be normal. And we're going to use little h for the faulty gene, for the mutated gene, which causes hemophilia. So this is hemophilia gene. So you've noticed I'm using capital H for the normal and little h for the hemophilia, so that straight away should give you a clue that normal gene is dominant and little h is the recessive gene. So that's pretty lucky, right? So hemophilia is not dominant, it's actually recessive. So let's have a look at a couple of scenarios. So let's say we have person with this kind of selection of genes in their cells. Well, you should be able to tell me quite a few things about this person. Well, first of all, are they male or female? Let's have a think about it. So I've got two X chromosomes. You remember in the previous set of notes, I said that that was a female, so I know this is female. And also I can see that both of her X chromosome contain normal gene. And so that means that this is normal female, so female normal. Okay, so a lot of you are going to fall into that particular category. So you're just a normal female with healthy, non-mutated sex chromosomes. Now, let's take the next scenario. What about this person? So H with a big X and a Y. Well, let's think about it whether they're male or female. So XY means that they're male. And they've got big H, and that means that they are normal. So this is a normal male. Now you probably notice that I have no letter written at all next to Y. Why is that? Because that particular gene, that gene for hemophilia or normal gene, it's only found in the X chromosome. So it does not exist at all in the Y chromosome. That's why I have no letter written next to Y. So that's really important. So make sure you're keeping track of that and you not start writing big H next to Y, for example. So next scenario. H and another H, but this time this is a small h. So what do you think is going on here? Well, first of all, I know this is a female again. Now let's think about it from point of view of hemophilia. Now, she's got one normal gene and one gene with hemophilia. Does it mean that this female is going to have the disease? Does it mean that she's going to go get hemophilia? Well, no, because the normal gene in that X chromosome is going to override the little h, the little faulty gene, and that's going to mean that she's actually living perfectly normal life. Her blood is clotting just as normal, and she's probably not even aware that she's got this faulty gene. So essentially, for all intents and purposes, this is a normal female, but we also call these females carriers. This is female carrier. So meaning that, you know, she doesn't have any symptoms, but she does carry that faulty gene. And she would only know about it if she's got some offsprings with hemophilia or if she gets genetic testing. So she might not be aware that she's a carrier. And the last scenario I wanted to kind of run past you is this one. How about this person? So what can you tell me about this particular individual? Well, again, same logic. So I know it's a male, X and Y, so I'm going to start with that, male. And I can clearly see they have hemophilia gene in the X chromosome. And here is the trick, right? Unlike my female carrier who had this second, H, second X chromosome with a healthy gene, Y chromosome does not contain that gene at all. So there is nothing here to override, to overpower this faulty gene. And that means that the male is going to have hemophilia. So this is going to be male hemophiliac. Hemophiliac. So this is a person who is going to actually have the disease. So in the case of hemophilia, basically, it's much worse than if you're a male. That's the bottom line, right? If you're a female, then you're most likely going to be all right. Now, I sometimes being asked, what about that kind of scenario, right? What does that mean? Well, potentially that would mean that this is female hemophiliac, but that would be extremely rare situation. So that would rely on a female carrier meeting and falling in love with male hemophiliac, so who has the disease, and they would produce babies, and you know, and you would have female hemophiliac in that scenario. I personally haven't come across this situation before. Have a look on Google and see if you can find a case like that. But you can appreciate that would be extremely unlikely, extremely rare. So we really usually kind of eliminate this particular genotype, and we don't really consider that, okay, because it's extremely unlikely, or at least it's extremely rare. So that's where we are. These are your 4 potential scenarios, 4 potential genotypes, and these are the 4 possibilities. So the first question I'd like you to look at is this question, question 16. Right, let me just zoom out slightly so we can see the whole page. So we're going to come back to questions 14 and 15, later, but let's start with this one because it deals with hemophilia. So here you've got a family diagram. So James and Mary, their parents, right? So they were married or decided to have kids, and their kids are Catherine and David. And then Catherine, in turn, met this chap called Patrick and had 3 kids of her own. So John, Anne, and Thomas were grandchildren of James and Mary. And then you've got the key to explain what each of the symbols mean. So you've got normal male, hemophiliac male, or a female. And your job is to identify genotypes of every person in this diagram. Okay, so next to each name, just pick one of your 4 options to say which genotype this person has. And so it's a bit of like a logical puzzle. So don't jump to conclusions, just think about it really carefully. So really consider what I was telling you about hemophilia and how it can be passed on. And think about, do a quick Punnett square if you need to, just to double check your answer. And just one other thing which I wanted to mention, for one of these people, you actually have 2 potential scenarios. We're not sure which one, so it's like a bit of a 50-50. So if you can work out both possible genotypes for this person, that would be amazing. But the rest of the people are pretty much clear-cut, so there's only one possible genotype there could be. Okay, so that's that question 16. And then moving on, we've got question 17. I would recommend you do that one next. And here we have a sort of real case scenario of Queen Victoria's family tree. So she was married, as you probably know from British history, to Prince Albert, who died fairly early, and then she was mourning him for the rest of her life. And she's got they had a whole bunch of kids. Obviously, contraception wasn't a big thing at that point, so they just had one kid after another kid after another kid. And apparently she loved sex and really was very keen on having this kind of intense relationship with Prince Albert, and hence all these multiple kids, multiple pregnancies. So all these kids also got married in turn. So let's try to count how many children they had. So we have to kind of be careful how we're counting with the diagram. So like where you have a line here, that means that's the partner of this person. So Victoria is the actual daughter of Queen Victoria and Prince Albert, but this person isn't, right? So we're just counting the direct descendants. So it's 1, 2, 3, 4, 5, 6, 7, so we've got 8 on this particular diagram. Is this right? 1, 2, 3, 4, 5, 6, 7, 8. Yeah. I think they actually have 9 children, but looks like one of them is not shown, unless I'm losing count. So you've got the information about who the hemophiliac males are. So these are the black squares. So these are showing. So all you need to do is write down from this diagram the names of all definite female carriers, not just the suspected ones, but the ones who definitely carried that faulty gene. So again, a bit of a kind of logical puzzle to have a go at. Okay, just a couple of kind of interesting facts to point out about this diagram. Sorry. As you probably know, people in royal families, they weren't particularly keen on diluting the royal blood. So if you look at this diagram pretty carefully, you can see that actually in these two branches of the family kind of connect up. So Irene actually married her her cousin. Sorry, I'm losing my voice a little bit. Not used to teaching so much, right, in class. And another interesting fact, which I wanted to kind of quickly run past, is the fact that there's a little bit of connection with Russia here. And obviously, I'm being Russian, I know a little bit of this part of history. So Nicholas of Russia, who's featured on this diagram, was the last Tsar of Russia. So he married a granddaughter of Queen Victoria, and they had 4 girls. And as you probably know, Tsars or kings, they were really keen on male heirs, and so they were really keen to have this boy, but they had girl after girl after girl after girl. And then finally they had a boy called Alex, or Alexis, as he's written here, and he unfortunately had hemophilia, and that was sort of a real disaster for that family. His mom then got into kind of trying to figure out a way of treating him, but of course at those times there was no cure, and so she went down kind of a route of inviting mystics and occultists and all these sort of strange people to try to treat him, and that didn't really work. And in the end, he never inherited the throne, because Russian Revolution of 1917 happened, and they were bundled up with their servants as well, and taken to a place called Yekaterinburg in the Ural Mountains. You can look up where it is if you like on the map. And they were put in the basement of a house, and then they were unfortunately all shot dead. And to kind of cover their tracks, the people who killed them, they took the bodies in the nearby woods, dug really deep graves, and then moreover put sort of chemicals, sort of something along kind of something similar to a bleach, basically, to try to disfigure the bodies. And so for many years those bodies were lost, and there were sorts of sort of myths about some of them surviving. Maybe some of you saw Disney cartoon called Anastasia, where one of his myths is kind of talked about this one of the daughters, Anastasia, surviving apparently. But it's actually not true, because they found in the 90s, they came across these graves, found them, and once they dug up the bones, then they needed to establish whether these bones indeed belonged to the children of Nicholas. And if you obviously trace their family tree back to Queen Victoria, that means that the modern British family is actually related to these guys. And so they asked for DNA sample from the modern royal family. I'm not quite sure who donated this sample. I don't think that was ever kind of established or at least talked about in the press. And so they checked this DNA sample and actually proved that those remains were indeed remains of Nicholas and Alexandria and their kid. And they were reburied kind of properly in St. Petersburg. So it's just a little interesting historic story. So anyway, your job here, as I said, to identify female carriers. Just a little clue, you should have 4 names on your list if you're doing it correctly. Okay, and then the final job for you to do is to go back to, as I said, questions 14 and 15, and those questions are looking at also sex-linked questions, but they're to do with Drosophila flies. And so when you're solving those questions, just be careful with the symbols, because they're using big W for red gene and little w for white. So when you're writing out all the genes, just make sure your big W's are really big and your little W's are really tiny, otherwise it's really easy to lose track of it all and come up with a incorrect answer. So anyway, good luck with that. Have a go, and see what answers you will end up with. Thank you very much.